Next section we're going to look at is section 4.2, which is on Rolle's and also the mean value theorem. Rolle's theorem gives it conditions that guarantee the existence of an extreme value in the interior of a closed interval. If we take a look at theorem 4.3, this is the statement of Rolle's theorem. We require that the function f be continuous on the closed interval a comma b and differentiable on the open interval ab. So it has to be continuous on the closed interval, but just differentiable within the interior of that interval, meaning the open set. Furthermore, if the value of the function at the endpoints is equal, meaning if f of a is equal to f of b, then there exists at least one number c in the open interval a comma b such that f prime of c is equal to 0. Okay. This is another one of those existence type theorems. We talked about a couple of these earlier in the class, but essentially what Rolle's theorem is saying is the following. Let's suppose we have a function, and let's suppose that it's a nice function. It's continuous on the closed interval a comma b and differentiable on the open interval a to b. If the value of f at a and b is equal to each other, then there exists at least one value c in the open interval a comma b such that f prime of c is equal to 0. Intuitively, think of it as follows. Let's suppose that the function was increasing when we started the interval. The only way that f of b could be equal to f of a is ultimately if that function will start to eventually turn around and go back to where it came from. So it has to eventually at some point stop increasing, and then it'll have to start to decrease. And in order to go from increasing to decreasing, that'd be a place where it has a positive derivative to a negative derivative. There must be some place where the derivative in between would have to be equal to 0. So that's what Rolle's theorem states. Okay. Let's take a look at example 1. They ask us to find two x-intercepts of f of x equals x squared minus 3x plus 2 and show that f prime of x is equal to 0 at some point between those two x-intercepts. Okay. So this is one we can actually kind of solve pretty straightforwardly. Thankfully, the x-intercepts, these are the solutions to the equation f of x is equal to 0. This is a nice polynomial equation. We can actually factor it. This polynomial would factor as x minus 1 times x minus 2 equals to 0. And so we get one solution would be x equals to 1, and another one would be x equals to 2. So according to what they're saying here is that there should be some place in the open interval 1 comma 2, so in between those two intercepts, where the derivative is going to be equal to 0. First of all, before we make such a claim, let's make sure we understand exactly why Rolle's theorem applies in this case. Okay. So this particular function f of x, this is a polynomial. We know that polynomials are continuous for all real numbers. Therefore, they'll be continuous on any closed interval or any closed set of the closed interval on the real numbers, and they're also differentiable everywhere as well. So this function certainly will be continuous on 1 comma 2 closed and differentiable on 1 comma 2 open, so Rolle's theorem applies. So by Rolle's theorem, there should be some place, at least one value c, such that f prime of c is going to be equal to 0, where c is going to be in between 1 and 2. We can actually solve for this. Let's take the derivative. F prime of x would be equal to 2x minus 3. Set the derivative equal to 0. 2x minus 3 equals 0. And we will get that the value we're looking for is going to be 3/2. So the value that was stated to occur in Rolle's theorem would be c equals to 3/2. And notice that that clearly is in the open interval 1 comma 2. Let's take a look at the next one. They give us the function f of x, which is equal to x to the 4th minus 2x squared. They say find all values c in the open interval negative 2 comma 2 such that f prime of c is equal to 0. Okay. This is another function. If we look at f of x, it's a polynomial again. So it's going to be continuous everywhere, differentiable everywhere. So certainly f of x will be continuous on the closed interval -2, 2, and differentiable on the open interval. One of the things that we would also want to check, according to Rolle's theorem, and we didn't check this in the last statement because we were working with two zeros, so we knew that f of 1 and f of 2 previously, they were equal to each other because they were both commonly a zero of that function. Let's just do a quick check here to make sure that f of -2 and f of +2 are equal to each other, because that's one of the requirements for Rolle's theorem. This is -2 to the 4th minus 2 times -2 squared. This is going to be 16 minus -2 squared is 4. Oh, excuse me. So we're going to get 8. So f of -2 is 8. Let's take a look at f of 2. This is going to be 2 to the 4th minus 2 times 2 squared. That's equal to, again, 16 minus 8, which is also 8. So it is true that f of -2 is equal to f of +2. F is continuous on the closed interval -2 to 2. It's differentiable on the open interval -2, 2. Therefore, Rolle's theorem guarantees at least one value c in that open interval such that f prime of c should be equal to 0. Well, let's go ahead and take our derivative. F prime of x is going to be equal to 4x cubed minus 4x. We're going to set that derivative equal to 0. So when is 4x cubed minus 4x equal to 0? Well, it's a polynomial equation. We can factor out a GCF, which is 4x. That'll leave us with the x squared minus 1. And then this becomes a difference of squares. It factors as x minus 1 times x plus 1 equals to 0. If we set each one of these three factors equal to 0 independently, we get one solution will be x equals to 0, one will be x equals to 1, and another one will be x equals to -1. It turns out that all three of these do lie within that open interval -2 to 2, so there's actually three such values of c that work in this case. They are in order -1, 0, and 1. Okay, just kind of a quick reminder about existence type theorems such as Rolle's is that they guarantee the existence of at least one such value c. And in general, as we just saw here a moment ago, oftentimes there can be perhaps more than one value of c. Okay, and we were kind of fortunate just based upon the way this function was set up, they were actually able to explicitly solve for them and see what those values were. Let's take a look at the next theorem. This is the mean value theorem. It's kind of an extension of Rolle's theorem. Let f be continuous on the closed interval and differentiable on the open interval a comma b, so same kind of initial criteria. The one restriction here is that we no longer require f of a to be equal to f of b. In general, if it's continuous on the closed interval and differentiable on the open interval, then the mean value theorem, the MVT, says that there exists at least one number c in the interval a comma b such that f prime of c is equal to f of b minus f of a divided by b minus a. And this right-hand side of this formula might look familiar to some of you. This is the average rate of change of the function. It's the average rate of change of f of x over the interval a to b. If you want to kind of visualize what's happening here, let's suppose we have a, We have b, so we have our closed interval. Suppose the function is continuous on the closed and differentiable on the open. Then essentially what this is saying is that there's going to be some point c between a and b where the rate of change, instantaneous rate of change, so this would be f prime of c, and the slope of that secant line, that's going to be the average rate of change of f over the interval. That line's going to have a slope of f of a minus f of b, all divided by b minus a. So it guarantees the existence of at least one such c. In other words, it's saying that there's some point in between a and b where the instantaneous rate of change of the function is equal to the average rate of change of the function over the whole interval. Let's take a look at one last example. In example 3, we have the function f of x, which is equal to 5 minus 4 over x. They say find all values of c in the open interval 1 comma 4 such that f prime of c is equal to f of 4 minus f of 1 divided by 4 minus 1. So essentially they're asking us to kind of verify the results of the mean value theorem. First thing we want to check is this particular function here. Notice that this function will have an issue at 0. It'll actually be undefined at 0, so it's not continuous nor is it differentiable at 0. But thankfully, the interval we're looking on, the closed interval, would be 1 comma 4, and this function will not only be continuous on that closed interval, but it will also be differentiable on the open interval 1 comma 4, and so the mean value theorem will apply here. Let's find the value for this right-hand side of this expression. So we need two function values. I need f of 4. This is going to be 5 minus 4 over 4, which is 5 minus 1, which itself is 4. F of 1, this is going to be 5 minus 4 over 1, which is 5 minus 4, which is 1. So this ratio, f of 4 minus f of 1, all divided by 4 minus 1, this works out to be 4 minus 1 over 4 minus 1, which is 3 over 3, or just 1. So there should be some place where the derivative, f prime of c, is going to be equal to 1 in that interval. Let's find the derivative. Before doing so, it might be helpful to rewrite the function. This is 5 minus 4. You can think of it as x to the negative first power. F prime of x is going to be equal to 5, bring the negative 1 power down. Negative 4 times negative 1 is a positive 4. Whoops. What's the derivative of a constant, everybody? We all know derivative of a constant 0, so that derivative of 5 is 0. Bring the negative 1 down, reduce the power by 1. And so we get this for our derivative, 4 divided by x squared. We're going to go ahead and set f prime of x equal to 1 to solve for those values c. So we have 4 divided by x squared equals to 1. Multiply both sides by x squared. We get 4 equals x squared. To get the x by itself, you would need to take the square root of both sides. So we get plus or minus 2. Only one of those solutions, however, would lie in the interval that we're looking for. So that's going to be the value positive 2. So the value guaranteed by the mean value theorem, where f prime of c is equal to f of b minus f of a over b minus a in this case is going to be c equals to 2. Oftentimes we're not going to get a lot of use out of it necessarily in our class. Sometimes there's an alternative way to kind of write the mean value theorem. It's also presented in the notes, but we're not going to make that a central focus for our class.